Hello and welcome to today's lesson on residual values, residual plots, and influential points. Okay, so we're really wrapping up our unit on bivariate data and regression. When we look at residuals, okay, residuals is the vertical deviation between the observation and the least squares regression line. Okay. What we know is the sum of the residuals always equals 0. If you think about our least squares regression line video that we went through, that lesson, we use the residual value when we're building the least squares regression line because we're minimizing the squared sum, or the sum of the squares, of all of these residual values. So when we were measuring that vertical distance, when we drew the line through, okay, what we were actually measuring is we were measuring the residual value. Okay, and what we want to think about is the formula that we're looking for. Our error, or the residual value for any point, is the observed, the actual y, minus the expected, that is the estimated y, from the least squares regression line. Okay, so when we're finding that residual distance, okay, it's the actual y value minus the estimated y value, okay, and we use that to be the residual for an individual point. Now, a residual plot, what we're going to do is we're going to find all of the residual values, and the calculator will be able to help us and do that for us. Okay, but a scatter plot of the residual pairs, okay, we can graph it based on the x value. Okay, so we're going to keep the original x values and graph the original, or the residual values, against that. And our whole goal is to identify, is there a true linear association? Okay, and it has to be a linear association that exists between the x and y variables for that situation. If there's no clear pattern, and when we talk about pattern, what we're really looking for is, some type of parabolic situation, either face up, face down, are the patterns that we're looking for. And we want to look for a clear pattern that would tell us that this is not a linear association. So let's look at a couple plots here and just be able to describe this. If we look at this first plot, okay, the first plot, we're plotting x versus y, okay, and we're looking at those values, and we should say this is the residual of y. We can look at this, and it's really kind of scattered. There's no clear pattern overall, okay, and that tells us that this is a good linear association between the two variables. But if we look at this second plot, okay, we can very easily see that parabolic look into the residual plot. Okay, so we know that this is not linear. Okay, now, one thing that you want to be careful of is make sure that you read the labels of the graph, because one thing that can be done is if a normal x versus y graph does not make a linear line, what we can start to do is we can start to do some natural logs of the values, so the ln of x, the ln of y, and that can actually straighten out the data. Okay, so if you start to see other variables introduced in the graph, okay, it may be a good association, okay, but it is not an xy linear association. It would be an ln of x, ln of y, or some mixture of that association. So make sure that you read the labels of the residual graph so you know what was being used to get that individual residual plot. Okay, so here, just looking at another example, okay, measuring the success of post-knee surgery. is looking at range of motion, and we're seeing, does range of motion, is it affected by age? Is there a relationship? And the one thing that we want to do, even more important than a strong R value, is the residual plot. This is your number one thing to look at on whether or not your data is linearly associated. Okay, so once again, we look at this, no clear U-shaped pattern one way or the other. Okay, so we know that there is a linear relationship between the age of the individual and their post-surgery range of motion that they have. Okay, so remember, your residual plot is that number one thing that we look at for the relationship overall. Okay, so now, how do we create a residual plot? Okay, a residual plot is something that is very time consuming. Okay, and we would want to use the calculator to do this for most of our work. Now, I just want to show the calculation. Okay, the residual is, remember, y actual minus y estimated. Okay, now, to be able to estimate the y, because I know that this first y value is 75. Now, if I want my estimated y value, that's when I have to use my least squares regression line. Okay, so my least squares regression line was 43.34 plus 0.460x. And to do this estimation, I'm going to use that first x value that pairs with it of 69. Okay, so when we're doing this, okay, we're going to find that estimated value, that single estimated value, and I'm just showing you how to do one. Okay, and then we're going to let the calculator do the rest of the work for us. So we have 43.34 plus 0.460 times 69. Okay, and we get an estimated value of 75.08. Okay, so we can see that for this data point, this line equation was a very good estimation of it. And now to get our residual value, it's the actual of 75 minus the estimated, and this point has a residual distance of negative 0.08. Okay, and if we were required to do that by hand, we would have to go through for every data point, you know, plug 90 into the equation, and then 89 minus that estimated value, and we would work our way through. Okay, but now, to do this, what we want to do, clear out, we want to plug in to our line equation, y1, okay, we want to plug in our least squares regression line, 43.34 plus 0.460 times x. So there's our least squares regression line in our plot. If we look at our original graph, let's go to Zoom Stat. Okay, so here is our actual data. Okay, we've got our actual data plugged in there. We can see the least squares regression line going through the middle. Okay, so we can see that coordinate point that we just estimated right here, very close to the original regression line overall. Okay, so now that we have the line in, we want to go back to Stat Edit, and we're going to put in a new list 3. And this list 3 is going to be our estimation values. So we have to highlight list 3 and hit enter. And what we're going to do is we have to go to our variables button, okay, y variables, function, y1. So I'm pulling that y1 equation out, and then I'm going to plug all of my x values from list 1 into it and hit enter. Okay, so you can see I've got now all of my estimated y values for that situation. So list 1 is x, list 2 is y, list 3 is the estimation of y. So now I have to go out one more list. I have to go out to list 4, highlight the list and hit enter, so it is getting into the input function, and this is where I'm going to build my residual value overall. So the residual is your actual y, list 2, minus your estimated y based on your linear regression equation, list 3, and then we hit enter. Okay, so we can see that first residual value matches up with what we calculated. And then what we want to do is now we're going to want to make the residual graph. So we're going to use our actual x values, stat, or we're going to go into the graph, stat plot. We're going to do a plot of list 1x versus list 4, which is the residual value. Okay, and then we just want to zoom 9 to zoom and get that statistical pattern. Okay, so here's our residual plot for this data. Okay, and we can see overall maybe a slight possible pattern, but it's not an obvious pattern. Okay, we really want to have a clear, obvious pattern overall, you know, especially when it starts jumping around at the end of the graph here. You know, we've got a value up here, a value down there. Okay, we can see that those values overall aren't fitting the overall pattern of the graph. Okay, so in those situations, we would say that a linear association for this data is appropriate. Okay, now we talked about the coefficient of determination before, r squared. R squared makes a little bit more sense when we tie it into our residual value overall, because it's the proportion of variation in y. Okay, so we're looking at that vertical or residual distance that can be approximated by the least squares regression line of x and y. Okay, so we're looking at kind of the goodness of fit. How well is the residual distances fit with this least squares regression line? Okay, now when we look at outliers, we want to be very careful when we're talking about the term outlier in a two-variable data situation. Because when you look at the data, something could look like an outlier, but it has to be an outlier within both. So when we come back to our original graphs, okay, there's only a couple points that we would even remotely consider an outlier. We've got this point down here and this point up here. Now this point is the furthest point in both directions. But what we notice is it really an outlier in terms of x? No, we've got a point right next to it. Is it an outlier in terms of y? The distance is a little bit bigger overall. Okay, but then we also want to look at the overall pattern. Does it have the largest residual value? And if it does have the largest residual value, and we can go back and look at our data list to see that, okay, the largest residual value happens at this point right here. Okay, we've got, oh, no, it is that value. 9.58 is the largest residual value, and it comes from that point where we have 98, 98, 98 on the homework, 98 on the final. Okay, we have another residual value that's, you know, fairly close. We've got a 7.86, a negative 6.96. So we have a few there that have a large residual value overall. Okay, now what we want to know about outliers and influential points is that point that has the largest residual value. If we go through and delete that value, okay, we want to look at the effects on the overall graph. So if we pull out that outlier or that individual value and we go back and calculate our linear regression, okay, we can see that sometimes the effect might not be what we're looking for. Okay, we took out that point and our correlation value was affected by that outlier being removed, but it did not increase. It actually decreased our correlation between these values. And the reason that that would happen is if we take out this point, what do we start to notice? Taking out that point starts to notice a more obvious pattern in our residuals, okay, which means that this might not be a linear association for this data. Okay, so that's things that we have to be careful of. Is in a regression setting, an outlier is a data point with a large residual, and an influential point, okay, is a point that when we remove it significantly changes the slope of the least squares regression line. So if we go back to this calculation, our slope originally was 0.460, and now our slope is 0.339. So taking that point out really decreased the slope of this line overall. Okay, now last thing for this lesson, what values are resistant to outliers? Least squares regression line, correlation coefficient, coefficient of determination, okay? And of these, none are resistant. Every one of these calculations is affected by an extreme value in either situation. Okay, and that concludes our lesson, and have a nice day.